So this is recapture what we talked about in the class. These are the temperature feature point, and 32 degree. Let's talk about the Fahrenheit first. 32 degree Fahrenheit is the ice point, and boiling point is 112 degree Fahrenheit. Actually, I myself is not quite familiar with this, but well, Imani, she knows. And then fever, and what temperature considered fever, and you say 102, and that's cool. And what's the normal temperature is around 98. So that's the Fahrenheit, and the temperature that we most familiar with here in United States. And so then Celsius. Celsius is nothing but absolute temperature rescaled. Ice point is 0, and 100 point is the boiling point. And with fever, and that's good to remember if you go to another Europe or Japan or China or any other Asian country, they use Celsius. So 37 degree is low fever, and temperature 37 or 36, and 39 is kind of high fever, 40 is even high, 42 you better watch out, it's a bit dangerous. Normal temperature is about 36 Celsius. And Kelvin, and of course, once again, 273.15 positive is ice point, and then add another 100 degree Kelvin, you get 373.15, and that's the boiling point. And then if you want to see what the absolute temperature from Celsius, all you have to do is add this magic number, 273.15. So we did a conversion between numbers. So this the formula is still in the previous slides and pages. And from Fahrenheit to Celsius, you simply do 5/9, which is a very almost half, and then parentheses Fahrenheit minus 32. So we tried with 0 degree, so you have 0. And then the other way around, backward, from Celsius to Fahrenheit, you have 9/5. Usually, and also just remember the Celsius is larger step. So therefore, and 9/5 is about 1.8. You multiply that, and then plus 32, because the 0 point is at 32 in Fahrenheit, and Celsius. So you, for example, 32 degree, that's a little bit low fever, and then you have 32 times 5/9, and then plus 32, and then you end up with something like 102.2. So you will get this question. These are simple questions. I'm sure I encourage you to get all of these questions answered correctly if you ever you've ever been asked these kind of questions. Converting between temperatures. Kinematic gas theory about temperature and gases. And you can start this video and simulations from these links if you had a real slice. And now let's recall the temperature is nothing but kinetic energy of atoms and molecules due to the translational motion, and that's energy. Okay, and that is done in the previous slides. Now we focus on a system of gas and its pressure. And what is pressure? And pressure, I think about its force on a surface and on a unit surface. The pressure will be force divided by the area. So, and now here in a gas system, the force is actually come from the collisions of these molecules on the wall. In a gas system, there are millions of molecules and collide. So therefore, pressure will depend on the kinetic energy, and in turn, kinetic energy depends on the temperature. Therefore, the pressure will depend on the temperature. And in your intuition, in your mind, see, the higher the temperature, the faster the balls will move, and then it will be hitting the wall harder, and therefore the pressure will be higher. So if everything else is fixed, you will expect the temperature pressure relation will be linear increase relation. So that's reflected in this equation, and this is called ideal gas law. And if you think about everything is fixed, so if temperature goes high, which means the speed goes high, we hit it on the wall and we'll have a stronger force. If everything else is fixed, and pressure will go high. And again, temperature go high, speed is high, and pressure go high. Now what about the volume? So the volume, the same, everything is fixed. So if the temperature is fixed, you can divide this volume to the other side, and you will see the pressure and volume has a reciprocal relation, which means inverse. Pressure depends on the inverse of the V, which means volume goes up and pressure actually goes down. And the other way, if volume goes up, pressure will go volume goes down, the pressure will go up. Because think about it, the pressure is nothing but the collision between these walls on the surfaces, and if the volume goes up, go bigger, and the box become larger, the area will be larger, and the same number of collision, the force will be less on each unit area. So you have more area, and therefore pressure will be low. Okay, so if the box is bigger, pressure will be low because you have same ball, but it will spread out in bigger areas. So that's fit our imagination. So if you have a volume goes up, then pressure goes down, and pressure goes up and volume goes down, and vice versa. Okay, so they have an inverse relation. Now here's another factor, and N is number of moles, or the amount of gas in the box. And what that has to do with the pressure, and you can think about it. So you have the box, temperature fixed, you have the same average velocities. Well, imagine you have 3 balls and they hit 3 times or something. And if you have 4, and you hit more, and the pressure will be higher. You have 10, you'll have more, and you have millions of them. That all really depends on how many of them there. So the dependency with the quantity of the gases to the pressure, or pressure dependency of the quantities between these two, P and N, number of molecules, and is simply a linear relation. So you have more molecules inside of the box with everything else fixed, more pressure, more molecule, more pressure. So that is natural thinking. So everything is within our imagination. We can know everything about this, and then so it's summarized in this relation: P times V equal nRT. So, and then what is that constant? So that is nothing but a constant. I get called a gas constant, and then its value is 8.314, and so that is fixed. So, this we will solve several problems, many homework problems, to use this equation. So even though this equation can be derived from statistical physics and from macroscopic models of the ideal gas, in fact, it is derived from there. But the details of our mathematical derivation is beyond this course. We are just focused on application of equation, given that we understand why this equation is true. So to summarize the details, P here is in units of pressure, meters per newtons per meter squared. That's units of pressure, and actually unit in Pascal. The volume in cubic meters. Actually, cubic meters is quite big, and N here is mole number and which how many moles. And once again, 1 mole of any molecule has this many numbers. Okay, it's a lot of molecule, but it's a fixed number. In other words, if you say I have 1 mole of hydrogen atoms, how many of them? Well, 6.03 times 10 to the 23. It's quite a lot. But if I have 1 mole of helium atom, how many of them? Same number, 1.03 and 2 times 10. Actually, 1 mole of anything has this many things. Okay, the same number. But immediately we think, well, how much 1 mole of something weighs? Well, depending on what it is. And 1 mole of hydrogen molecule, hydrogen atoms will weigh 1 gram. Okay, hydrogen uses a standard. But 1 mole of hydrogen molecule, which has 2 hydrogen atoms, will weigh 2 grams. All right. And what about 1 mole of water molecules? You know, water is H2O. So H is 1, another 2H is 2, and oxygen has the weight of 16. So 1 mole of water weighs 18 grams. But they have how many water molecules, how many H2Os, and same number, 6.03 times 10 to the 23. So 1 mole of anything have the same number. That number is called Avogadro number. 1 mole of anything has this number, but they have different weight. Okay, and it's easy to remember. The weight is just its molecular weight and turn into grams. So, for example, the molecular weight of hydrogen atom is 1, and therefore 1 gram. Molecular weight of hydrogen atom is 2. Molecule is 2, therefore its molar weight is 2. So molecular weight of helium is 4, and therefore molar weight of helium is 4 grams. So molecular weight of oxygen gas is 32. Therefore, the oxygen is molar weight of oxygen is 32 grams. So and so on. You simply turn the molecular weight into grams. So that would be a different way. But in any case, 1 mole of anything has this number of molecules. Remember that firmly. And that number is called Avogadro number. So that's the mole number, how many moles of this. And then temperature, again, is in Kelvin degree, and molar constant, we already said 8.3 mole and Kelvin. And also Avogadro number, and that magic number is 1 mole of anything has this number, and 1 mole of anything has exactly this many molecules. Okay, and this is the note on one of the classes, and we just look at the ideal gas law and try to appreciate it. And 3 quantities of the gas, or 4 quantities: pressure and volume and temperature and the amount in mole numbers. So mathematically we view this. So if you think about pressure's relation with temperature, you think about one is fixed, and then you will say, well, pressure is actually a function of temperature, with everything else fixed as constant. Implies that volume and molar number and of course gas constant is fixed. And then you will expect that linear relation goes like temperature goes high, pressure goes high, everything like that, just straight. And temperature goes to 0, pressure goes to 0. You can imagine the atoms stop moving, and then there's no hitting on the wall. The pressure goes 0. So now, if you solve this V into the other side, then you try to look at the relation between the pressure and the volume. You have an inverse relation, pressure and volume. So divide this to the other side, and RT divided by volume. Then this relation is reciprocal relation. So volume goes up, and then think about it. Everything else is fixed. temperature and amount, and then volume goes up, then you will have bigger area on everything, and then you have the same force because you have everything else the same, and the area same force, bigger area, the pressure will low. And of course, if everything, the volume goes small, then you have small area on the wall, and then same force, then the pressure will go high. So it's an inverse relation. So it's put like this. Your volume goes up, area gets big, and pressure goes low. And volume goes small this way, and of course, everything's squeezed, and the pressure goes high. So that's just this trend we talked about in class. Well, in one of the classes, we re-enhanced on the concept of PV equal nRT, the ideal gas law, and think about introduce the effect of the gravity. So, and air molecules are pretty close to the ideal gas, but they're, if you look at a small box of it and still follow the ideal gas law. But when the gravity is introduced, and imagine on the Earth's surface, there were molecules, and they are actually, and you were asked why it's not going away. So it's going that fast at 300 meters per second, like speed of rockets, and goes very fast. But because it would go flying away of the to the outer space. But why is it not flying away? Because the gravity attracting it. So there are two factors. One factor is they're high speed moving randomly, but on the other side, there's another factor, which is the gravity as you bring them down. The balancing effect that will all attach to the Earth, but does not fall down to the ground because they kick out into space, then they spread out or into about a certain distance above the Earth. But that distance, if you look from the bigger scale, is not very high. But of course, compared to us, each of us is just a few feet tall. It's very, very high. Looks like the air is infinitely high, but actually it's not. It's not that high. It's about 10 to 15 miles. Okay. So you can think about it's have a column of air covered, or a blanket covered us. So, and then its weight will be all on a ground. So, and so it's gradually the pressure of the air gradually reduced and in an exponential format. Okay, and go to the higher you go, the lower the pressure at the same temperature. But at the bottom, think about all that weight of the molecules on us, and that has the atmosphere pressure because of the weight. All right, of that. So then at the bottom, how much is that pressure? That is called atmospheric pressure due to air. And if you think about 1 meter squared, and that is about 101 times 3 newtons per square meter. So this square meter, all that air is on top of us, and we will have this much force on 1 square meter. How heavy it is? And remember, I asked you in the exam, how strong is a Newton? Like a little apple holding, and 1 square meter will have this many apples, 100,000 apples, quite strong pressure. Well, if you ask you, and why it's not moving, but of course it's in all directions, isotropic. So that's the reason for. So that's because of the gas, and because it has all the weight of the molecules on us, so they have the atmospheric pressure. And so this pressure will go low and low, but slowly, and get up. And of course, because the standard atmosphere pressure is also same number, but it has, since it's depending on the height on the top of building, top of a very high building, the pressure will be lower. Then where the standard is at the sea level. at sea level and at 0 degree Celsius, and the pressure, so that's the pressure is the standard atmosphere pressure. All right, that's this class, or it was that class. Okay, what we did. Okay, in this class, we actually reviewed a little bit chemistry, or how to understand how to read the periodic table, and how to understand the atomic structure of the every elements. So this is actually a review if you have taken chemistry. So just you have a core has protons and neutrons. Okay. And then proton number is actually number of protons is actually the name, tied to the name of the elements. So if you have a core have only 1 protons, and then that's element number 1, you get hydrogen. So on each square in the periodic table on top left corner, and there's a number. And actually that's the number of protons, and also you call number, it's also called the atomic number, and that number is like your number on your jersey. So your player number 1, player number 2, and so on in a team. But in this periodic table team, number 1 is hydrogen. So actually same time number of protons. Then in the middle is the name, it's called hydrogen, and at the very bottom is the weight. Okay, then the weight is 1. Now, if you have helium, and then you will have this picture. There are 2 protons, and then therefore on the top left you will have 2, which means element number 2, helium, and He, that's symbol. And then you have a number, so what it is called? It's called helium. And the very bottom, and it's called a mass number. Okay, it's basically 4, but sometimes it has a little bit of decimals, and that is, but this number at the bottom is called atomic weight, or how much they basically is counting the numbers. So 1, 2, 3, 4 for helium, so you have 4, but 4.1 or 4.2, but the bottom number, at least for the first 2 row of periodic table, and pretty close to a whole number. Once again, the bottom number is atomic mass, and it's pretty close to a full number. For example, helium is pretty close to 4, so therefore it's 4 point something. So that number is 4, which means there are 4, 2 protons, 2 neutrons, and that number is, if you round this number to a whole number, and it will be, we call it its mass number. If you call it mass number, it's 4 exactly. But if you say atomic mass, it's 4 point something. You can read the periodic table. So once again, if you say mass number, is 4, 1, 2, 3, 4, 2 protons, 2 neutrons. If you say mass of helium is 4 point something, but you round up that number, it goes to 4. So remember what when you are asked a question, you listen exactly what is asked. If I ask you what is atomic weight for helium, you will say, you will read the periodic table, all the decimals, 4.022, something like that. But if I say what is the mass number for helium, you round up that number, just say 4, just indicating there are 4 particles. Once again, neutron and protons have approximately the same mass. Once again, neutron and protons has approximately the same mass, but if we, for our practical purpose, especially for chemicals, and so then, in fact, so just 4, they have they'll count 4 numbers. So therefore, so 2 for helium. So then what? Look up. Okay, now here's the test. What's for lithium? Okay, number 3, and so number 3, and what if then you have here something like 6.9 and with mass, which means 6.9 times of the hydrogen's weight. But it round up to a 7. All right, if I'm put over here is a 7 mass number. So if I ask you how many neutrons are in lithium core, you will say 4 neutrons. Why? Where did that 4 come from? Because the total is 7. 7 minus 3 protons, and then what's left is neutrons, which is 4. So hope that makes sense. And then these 4 quantities have the same number. Remember, the weight of a hydrogen atom has this much weight, 1.67 times 10 to the negative 23. So that's weight. Okay, and this number, or approximately this number, called 1 atomic weight units. Okay, this weight is called 1 atomic weight. It's very small. But if you have 2, then of course 2 atomic weight units is very small. And so now, what about the weight of a neutron? Same number, of course, maybe 1.66 or something, 1.662, but same number. And 1 atomic unit is weight. So the 4 quantities when people use referring to in any practical purpose, and for us, we are not getting to detailed nuclear physics or something. And these 4 refer basically the same. So remember, weight of mass of hydrogen atoms and 1 atomic unit weight, and this number, and the mass of neutron and mass of proton is all referring to the same weight. So therefore, simply it was 1 atomic units. And the 1 atomic units is some number, and you can dig up on Google, and this number is all about the same weight. And it was listed here on the bottom line of every element. How much weight is that, how much mass is the atom is measured compared to how many of these weight. So therefore, this is that used as a units. Or you can say how many times heavier than the hydrogen atoms. So for example, helium is 4 times, lithium is 7 times, and so on. Oxygen is 16 times of that. So it's atomic mass units. So atomic mass units and weight of proton, weight of neutron, and 1.67 times 10 to the negative 27 is all more or less the same number. Well, if you are after the difference between these 4 numbers, and then great, you want to be a great scientist, I encourage you to study physics, nuclear physics, and think why there is slight difference between the actual counting numbers, and that will involve in nuclear reactions and really beyond this course. But that's what I have to offer here. Just think about these 4 concepts are the same number. Once again, the weight of a hydrogen atom, and weight of mass of a proton, and mass of neutron, and atomic units mass, and 1.67 times 10 to the negative 27 kilograms is the same number, right? Well, for important concept, it doesn't hurt to have some repetition. So now let's talk about this molar number. I have said that 1 mole of any substance has this many numbers. Why is this magic number? So it's not really magic at all. Let me illustrate about this. So you say, well, if I want 1 mole of hydrogen, 1 gram of hydrogen. So if I have 1 gram of hydrogen, so you have 1. Okay, and if I want to say how many of hydrogen atoms are there, but I know the hydrogen atom has the weight of, that's atomic weight, basically approximately 1.67, okay, and times 10 to the negative 27, so we just talked about kilograms. That's also the number of neutrons, the number of protons, and so kilograms. So, and times 10 to the, of course, if you times 10 to the third, right? 10 to the third kilo. Okay, and if you divide this 1 over, you use your calculator. So 1 gram of hydrogen, and you divide by this units, which means 1 gram is how many of this little weight? Well, it's a lot. You invert. Each hydrogen atom weighs this much. Well, okay, and but then 1 gram, and you divide this, it will have this many hydrogen atoms. So this many hydrogen atoms, right? So think real hard. So then you get this. You can do the math. You get this 1 divided by that much. And then, so then this magic number is really not really magic. It's nothing but a unit conversion. You know hydrogen atom weighs this much. And then if you divide 1 gram of it, and then you have this. So then I ask a question a little bit reversed. How much 1 gram of hydrogen, 1 mole of this number, we call this number a mole number, 1 mole. Okay, how much 1 mole of hydrogen weight? How much this number of hydrogen weight? And the answer is 1 gram. Duh, you just made that way, right? So, okay, this many hydrogen atom will weigh 1 gram. Okay, and so that's called 1 mole. Therefore, 1 mole of hydrogen atom will weigh 1 gram. Okay, which means this many. So this is called 1 mole. Okay, this many. Okay, now this many 1 mole of hydrogen atom weighs 1 gram. Because why? Because that's simply a conversion between units. You get this. So now, if you have a molecule, hydrogen molecule form an air. Okay, H2. And so if I say, well, this many hydrogen atom weighs how much hydrogen molecules? H2. Okay, you have this many, 1 mole. So 1 mole, which means that many. Of course, you have double this weight. Therefore, you say, well, this hydrogen molecule of 1 mole will be having 2 grams, right? Because this many is 1 gram, and then this many is 2 grams. So now, same idea. If you have H2O, this one, each one has 1, but that one has 16 atomic weight, which means 16. That one has 1 times 2. So therefore, 16, that is bigger. So 1 mole of this, which means this many of this. So if you 1 mole of this weighs 18 grams. All right, 18 grams. 18 grams is quite a lot. So it's water is like several big spoon of water. So 18 grams. So not 3 or 4. So then how do you? So then 1 mole is the mole number is simply a conversion between grams and atomic units. So that's Avogadro number. Therefore, naturally, to turn the number of mole into the atomic molecular weight is pretty straightforward. You simply do the atomic weight turn into grams. So 18 atomic weight will turn into 18 grams. So we have here some examples. Okay, the kind of molecular weight, okay, is like molecular weight or more molecular weight or molecular mass. Okay, you turn molecular weight to molecular mass. All right. So for example, you have methane, which is carbon H4. So if you look up carbon, the molecular weight of carbon, atom weight of carbon is 12.001. In this case, you really want mass. So which means there are about approximately 12 of these mass units. So it's one of them. Okay. So therefore, you turn this into gram. You will say 12.001 gram of carbon. And then you have hydrogen, which is 1.007. You look at from the periodic table, it's this exactly this one. But you have 4, so times 4, you have this much grams. Therefore, molecular mass of this, of methane, is carbon 12 and H4, and you have 16. So 4 of this and plus 12, 12.11 plus 4, you get 16. So that's the molecular mass or molar mass. So molar mass of the methane is 16.043 grams. Okay, gram is not the sizable units, but atomic units is very small. But this one is measured in atomic units, and so that's probably you need a molar number. So simply convert this number to mass number. So here is another example. I don't want to go into it. And you have H2, 1H4, and so what if you have carbon-14 methanes? Carbon-13 would be not C12. Okay, C12 you can have C13. So you do the same, where the molar mass will be different. So that's the idea of a molar or molecular weight or molar mass and what's their relation. Okay, molar mass is how much mass is of 1 mole of some substance. Okay, and that's a very practical concept. Once again, molar mass usually in grams. 1 mole of something, how many grams in there? So for example, molar mass of water is 18 grams. It's like 2 spoons of water. So that's the review in one of the classes. And then standard atmosphere pressure, and is this much. Imagine 1.1 over 0.3 kilopascal, and it's because of all columns water, columns of gas. And of course, pressure changes with temperature. Then this number is this much. And the standard has to be 0 degrees Celsius and 273.15 Kelvin, and 1 mole. And also at the standard, using ideal gas, 1 mole of gas, any gas, at the standard pressure, we will have 22.4 liter. Okay, and so that's the summary. This is a review or looking at the molar number or Avogadro number or standard atmospheric pressure from a slightly different angle. And plus you learn how do you calculate the molar mass from atomic weight. Okay, and look it up from periodic table. We also discuss units and measurement of the pressure. So standard units is Newton per square meters. That's called Pascal. In fact, that's very small units. Think about it. A Newton is like a little apple holding in your hands. Okay? But 1 square meter is quite big. Okay? And then, of course, 1 Pascal, therefore, is a small pressure. But normally, we don't use Pascal as units. But so nevertheless, that's the standard units. It's Pascal, 1 Newton per square meter. So more often we use called PSI as our units, but pounds per square inch. Actually, that's a relatively large pressure. So you think about a 1 pound per square inch, 1 pound force per square inch is like 6,000 some Pascal. You can say around 1. That's quite 1 pound square inch, and you have 1 pound. So you feel how strong that is. So then you have that, and then there's another units which is interesting. It's standardly used in weather forecast called 1 bar. Actually, it's a large pressure, and it's like at 100,000. Okay. But imagine the atmosphere will give you pressure, and your surrounding have pressure of the air by default, and it's 101. So therefore, how strong is the bar? And roughly, you're going to say roughly 1 atmosphere pressure. That's why probably people call it 1 bar, because the 101 is 1% difference from if it's 101.3, and that's basically atmosphere pressure. So therefore, 1 bar is 100,000 Pascal, exactly. Okay, that's the definition of a bar. But how strong a bar? And it's basically 1 atmosphere pressure, a little bit less, because atmospheric pressure will be 101.3, 101.3, something up and down with temperature and pressure, but roughly this number. So 1 bar is atmospheric pressure, roughly. And then, of course, standard atmospheric pressure is about 101.3 kilopascal. So, but then convert to PSI is like 14. How strong, if you want to have imagine how strong the atmosphere pressure pressing on you, it's like if you have the tip of the thumb will have like 6 or 7 pounds, or because 1 square inch will have 6 or 7 pounds. You're holding your finger with 7 or 6 pounds. That's not a big pressure, but quite significant. So that's this. And another quantity is we frequently use, we measure the pressure on the tire, is called the gauge pressure. Because you don't want to confuse yourself, or you don't want to keep on saying, oh, there's by default, how much the pressure is actually higher than the regular atmospheric pressure. So therefore, the gauge pressure is actually the amount that above the normal pressure. So you say you blow up a balloon, so the pressure is actually higher inside the balloon. So if you gauge that pressure, which is 14 psi and plus say 14.7, that will be 0.7, 15 will be 1 above atmospheric pressure, and 20 will be 6 psi above atmospheric pressure. Because therefore the gauge pressure is how much is above atmospheric pressure. Okay, that's called a gauge pressure. Once again, the gauge pressure, you use the pressure gauge or the meter, and you measure pressure of your tire, is not the absolute pressure, is how much is above. So then you have this relation. So you measure from the gauge, say 5 psi, then what is the real pressure is 5 plus 14.6. That's the real pressure. So for example, and here, if your gauge says 32 psi, that's what's the pressure of the tire. Okay, but actual pressure is higher because there's already by default the 14 psi there. So plus this, your 32 psi, the actual pressure is 47. So 34 plus 14 is 47. That's a pretty simple idea. But just the idea, the gauge pressure is how much above the atmospheric pressure. Or mathematically, it is the other way. The absolute pressure, or you can say the real pressure, is the gauge plus whatever already there, the atmospheric pressure. The first 2 questions of this exercise is about molar weight and moles, the concept. Let's talk about the first one. Number 29. A sample of Q copper has the mass of 12.5 grams. So imagine a piece of copper, like a key or something, copper key, golden. Calculate the number of moles. Okay, once again, moles is a certain number, and that number is a large number, but 6.02 times 10 to the 23. 1 mole of anything has this much number. So, all right, so then how do you do that? Then you will see 1 mole of anything has this number, and then you want to know the mass of 1 mole of copper. And to do that is a very straightforward procedure. And don't ask why, because I already explained. The way to do it is to look up a periodic table, look at the square for copper. At the very bottom, there's atomic weight units. So it's 63.5 atomic units, which means the copper atom is about 63.5 times of the hydrogen weight. That's atomic units. And that weight is very small, but that's more or less the same number. But then to turn 1 mole of 1 mole of that, how many grams? just use this number literally, turn into gram. So 1 mole of copper has 63.5 grams. So it's quite big, okay? And then, so then you will say, well, how many moles of 12.5 grams is it? So 12.5 divided by this is like less than 1 mole, 0.197 mole. So that answers the first question. So to summarize, you get the mole number, and by dividing the mass with the molar weight, this is called a molar mass of them. To get that, get a periodic table with the bottom number, 63.5 atomic units. Just directly turn that number into grams. That's how much the atom will weigh. The 1 mole of this copper will weigh. So 65 grams divided by that. So then division, you get a mole number. Now the second question, copper, how many copper atoms in there? So that's easy. That's simply multiply the number of moles with that magic number, 0.197 times 10 to, so which is large number. I don't need to multiply that. So so number 30. So I'm not going to work out. It's the same idea. So formaldehyde, right? So it's one kind of chemical. I think it's used for cleaning in a lab. I'm not 100% sure, but the point here is we want to know the molecular weight or molecular mass. What does that mean? Each molecule, how much it weighs in atomic units, and that number directly turn into a grams. That's the molar weight of this type of material or some molecules. 1 mole, how much it weighs. So calculate the number of moles. First, we need to know molar mass, how many grams. So then you look up the carbon, which is something like 12.004. So remember that. Hydrogen is 1, so there are 2 of them, 2. So 12 plus 2, roughly you get 14. So oxygen, you look at it, and it will be something like 16. But add those numbers, including decimals, exactly. So that is how much each molecule will weigh in atomic units. Interestingly, use that number in atomic unit, turn that into grams. That's how much mass is of 1 mole of CH2O. So that's easy to calculate. Once you get that, so then you use that. Then you have 275 divide molar weight of this molecule, and then you get how many moles in this. And then how many molecules, and then you choose how many moles times that magic number, 6.02 times 10 to 23. Hope this helps. Now, in next page, we'll work on these 2 questions, 31, 32, 33. Well, we continue work on our homework problems. Number 31. Okay, it's here. 1 mole of oxygen gas. So we remember 1 mole, which means N equal 1. So that many. So at the pressure of 6.00 atmosphere pressure, which is 6 times of that pressure we are experiencing with the air. But of course, it's a container, must be in a container, and a temperature of 27 degrees. So it must be in some kind of a oxygen bottle or something. You have oxygen bottle, like kind of scary. And so the question is, so at this 6 atmosphere pressure and 27 degrees, and if the gas is heated, you want to heat this, okay? See if the oxygen bottle is under the sunshine, right? Under the sunshine, so of course it's heated up, and until the pressure triples. When the heat up, the pressure triples. And what is the final temperature? So that is actually a realistic question. If you want to get into science, biology, chemistry, or somebody work with substances, you should know. So 6 atmosphere and pressure, and then at this, and then the final stage will be a higher pressure and obviously higher temperature. How do you solve this question? So now back here, P times V equal nRT should always hold true to start with, and the ending point is always the same. So now which is P1 and T1 to begin with, and then we have P2 and T2 to begin with. So P1 is 6 times atmosphere pressure, and T1 is 27. So to use the ideal gas law, you must convert that into a Kelvin. So simply add 275. So starting temperature 300.15 Kelvin. So then P2, we want to triple the pressure. So P2 is 3 times P1. So of course it's 18. But we just leave it there. So we're not told what is exactly the temperature. So then now if you have P1, P2, and if you divide this, so P1 equal VP, let's assuming that the contents, the volume didn't change, the gas didn't leak, so it's between pressure and temperature. So your P1 equal V nR T1, and P2 times V nR T2. So you divide these two equations, you get P1 over T2, T1 over T2. And they are in proportion. So then it's easy to convert. So a couple of steps of math, you solve this T2 in terms of T1, P2, P1, then you end up with this. So T1, 315, come down from there. And then 3 times P1, you can spell out. Bottom one is 6, top is 18. So, but this cancels out anyway. Therefore, the temperature is simply 3 times higher. So from here, it's simply a pressure. If the volume is constant, the pressure is simply proportional to the temperature, or vice versa. It's proportional. So if the pressure is tripled, temperature is also tripled as well. Okay, so that's this part. Number 32. And again, container holds 0.5 cubic meter of oxygen, okay, at absolute pressure of 4 atmosphere pressure. Absolute pressure. It has to be absolute pressure. And a valve is open and allow the gas to drive a piston. You know what the piston is, like a disc on one side connected or welded a stick, and typically that stick at the other end of the stick is connected to a wheel. Sometimes it's called a flywheel. And this is typical main mechanism of how engine works. When the gas expands, it pushes the piston, and the piston on the other side, the rod spin the wheel. So, but let me see. So there's it over here, and the gas container here, and there's a piston. So now here's the valve open, so it pushes open. The later it will, this is bigger, and then they push it bigger. So the question is, of course, here is a higher pressure, and then push it lower pressure. And is the volume bigger or small? You tell me. It's bigger. All right. It says temperature stay the same, and then what is the new volume? So what is the new volume? So again, ideal gas equation: P times V equal number of moles and the gas constant T. But in this case, temperature stays constant. It is the pressure that pushes and does the work and expand, and then of course pressure dropped, right? Because this gets bigger. So how do you solve this one? P1, again, this always holds true as long as the gas didn't leak. Okay, P1 V1 P1 equals nRT, but that stay constant. But then it changed later on. It become P is also equal P2 times V2. P2 is smaller. Then V2 must be bigger, right? Because to make the product the same as before. So then that's what I have here. P1 times V1 is P2 times V2. And if you move the terms, dividing P1 to the other side, dividing V1 to the other side, you get this ratio. What you're going to have is V2, you solve this, V2 is V1 times P1, P2. When you do a homework problem, don't get the order wrong, but that will require you to review your math or simply algebra and how to manipulate the terms. So you divide one object to the other side and to divide, and one move to the other side and to multiply, and vice versa. So you get this P2 equals V1 times P1 over V2, and then so now P1 is actually 4 atmosphere per P, and then later on P2 is 1, so 1 over 4, and P1, so 0.5 times 4 over 1, and it's 2. So that's, here it started with 4 and 1, but then the volume become 1 to 4. So this question, I like this question, because so pressure go from 4 to 1, and then the volume must go from 1 to 4, right? So that to maintain the product the same. So 1 times 4 times 1, and then 1 times 4, and will be the same. Okay, so that's problem number 32. So gas expand, pressure reduces, but volume increases. All right, number 33. Another question involved the ideal gas equation, but this time the unknown is different. Unknown is number of molecules, nRT, and that number is n. So PV equal nRT. There are actually 1, 2, 3, 4 variables, one gas constant. So now in this case, P, V, and T are known, and so we want to know how many n's are there. Okay, basically you solve this. So PV divided by R divided by T equals that. We are talking about 33 once again. So that's the same equation, but we know pressure, starting pressure, volume, 1 centimeters cubed, and gas constant we know, and temperature is 20 degrees or convert to Kelvin. But we solve how many moles are in there. We divide this to the other side, we get moles. So now here I didn't complete, but so let's see. Volume is centimeter. Remember, it takes cubic meters. Okay, so it was 10 to the negative 6 cubic meters. That's very small volume. But this is actually 1 milliliter, 1 cubic centimeters. Those of you who are in biology must be very interested in this. So this is very small volume. 1 atmosphere pressure, but standard atmosphere pressure is 1.01 times 10 to the 5th, very high, Pascal. Atmosphere pressure is this much. And then at 20 degrees Celsius, and then you must convert that to Kelvin. So 20 degrees plus 275 is like 293.57. So you have, once again, volume, pressure, and temperature. Okay, you have 3 quantities known in this. Now the last unknown is its n. You divide this by the other side, and I don't want to show the details, but you end up with this very small amount, less than 1 mole. So 4.1 times 10 to the 5th mole. In fact, this question has some realistic event, realistic impact or usefulness, because in medicine profession or lab technician, they usually use milliliters. So milliliter is about, this size is called milliliter. And you say 1 milliliter of air, well, air is everywhere. How many molecules are there? Okay, and then you have to know how many moles it is. So that's the result. Normally 1 milliliter of them, you have 4.1. That's how you calculate it. And later on, if you take some other exam, people may ask you to calculate this. How many moles are there? 4.1 times 10 to the negative 5. Pretty small amount. And there's how many molecules of air in there. So then you will see, of course, the ideal gas. Something like how many molecules? 2.46 times 10 to the 19. So instead of 23, multiply this small number with that number, 6.02 times 10 to the 23, called Avogadro number, and that is 23. So now it's 10 to the 19. So that's this. And then, so that's the first part of this question, A. And N, number of moles, is 4.1 times 10 to the negative 5. That's how you simply solve n from the ideal gas equation with the other three quantities known. So B, and I leave this to you. So, but then if the pressure of this volume reduced to that, how can it reduce? So everything else, the volume is the same, all right, and also the temperature is the same. So what can happen? We'll reduce pressure. So think about it. The volume is same, temperature is same, pressure is reduced. If the pressure reduced, which means there's a leak or let go of the air, so there will be a leak. Okay, so what? How many moles of the gas remain? So then you will do the same calculation, plug in the pressure and plug in the temperature, and solve how many moles of it, and then find the n. All right. Okay, so that's this exercise. Hope it helps. Okay, let me know if you have further questions.
Ideal gas law questions. And number 22. The gauge pressure in your car tire is 2.5 times 10 to the fifth Newton meter squared. That's Pascal. And at a temperature of 35 degrees Celsius. So you have pressure and temperature at one situation. Actually, you drive to Alaska. And later on, Alaska is very cold, and then the temperature dropped to negative 40 degrees Celsius. Then, of course, when the pressure temperature is lowered and the pressure drops. So now we want to know what is the exact pressure. So that we're going to hire the ideal gas equation. So then this is the ideal gas equation. So first of all, the ideal gas equation takes only the Kelvin degree. So gauge pressure is not absolute pressure. So gauge pressure has to change to the absolute pressure. So gauge pressure is actually on top of atmosphere pressure. So you plus atmosphere pressure, so that is 3.1 times 10 to the fifth. You get the real pressure, the absolute pressure. That's P1 to begin with. And the temperature, you also need to convert to Kelvin. 35 degree Kelvin is 35 degrees Celsius, excuse me, is plus 273.15 is 308 Kelvin degree. Later, the temperature dropped, negative 40 centigrade or Celsius, and converting to Kelvin, it is 233.15. So both temperature is converted to the what's required in ideal gas equation. This. Now what to be found is P2. Okay, and P2 in absolute pressure first. So now, since this equation has always been satisfied, and you have P1 times P2 V and R T1. P2 V and R T2. Notice that V and NR never change. Only temperature and pressure change. So you divide them, then you get P1 over P2 divided by T1 over T2. What happened to others? They cancels out. Okay, and then you solve for P2, just a couple of steps manipulating. You move P to the other side and move T to the other side and move T down. So therefore P2 is P1 times T2 over T1. And then you plug in numbers. So that's the P1, the initial pressure, and this is the ratio of the two temperatures. So this is initial temperature, and this is initial temperature, that's the final temperature. So it's less, so the pressure becomes less. But remember, we are asked to find out the gauge pressure, the final gauge pressure. But then this is absolute pressure, so the gauge pressure 2 is nothing but the absolute pressure and take away the atmosphere pressure. So then you just get that, and whatever you have is 1.15. That's the gauge pressure, which means later when it gets cold, you will measure with the pressure gauge, you will get 1.15. Then of course you can convert that to PSI if you want. So to summarize this problem, and you have an initial pressure, which is absolute pressure, and then you change to gate pressure, and then as temperature as well, and then later it becomes cold and pressure will drop, and this ratio between pressure and temperature are exactly the same. So that's how you get it. So number 23. Okay, this question is actually again about gauge pressure and absolute pressure. So you know the fact that what the pressure you measure with the pressure gauge to measure the tire pressure or some pressure is actually what's on top of the regular atmosphere pressure. So convert this absolute pressure to the gauge pressure and also convert the units. Pound per square units. This is actually like a PSI, pound per square units. So first step is convert to the gauge pressure. So absolute pressure, that's what's given, and minus 1.01 times 10 to the fifth. So that's, well, just remember 10 to the fifth is always there. So you minus that and you get that. It's less. So, and you remember absolute pressure is always higher than the gauge pressure because you don't count the whatever pressure is already there. Okay, and so now it's a matter of unit conversion. So the trick for unit conversion is you convert patiently whatever the target unit is, from Newton to pounds and from meter to inches squared. Newton is actually a force units. All right, actually the kilogram force. So what does kilogram force means? Is the force that 1 kilogram will sense, and that's called a kilogram force. In fact, that is nothing but 9.8 newtons. So 1 newton divided by 9.8, so you get 0.102 kilogram force. That's why sometimes people simply drop this force and you say 1 kilogram force, which means just 9.8 newtons. Okay, so, but that's true only on the Earth's surface. So it's 1.102 kilogram force. You can simply say kilogram. Okay, that may confuse the concept of mass and weight. We repeated that for many times. So we just call it kilogram force, and then 1 kilogram, and it will be 2.204 pounds. That's the mass units conversion. You can easily find this, which means pounds are less, almost half, less than half of the kilograms. So therefore, kilogram force is actually 2.204 pound dash force. Okay, and actually pounds force is like how much force, the gravitational force, 1 pound's mass will sense on the Earth's surface. Sometimes people drop all this statement. It just say 1 pound's force. Okay, so 2.204. So then you plug all this in here. So gauge pressure is that to begin with. Newton, you get this, and meter square. If you count meter square to square inch, so easily to convert, and 1550. Always remember meter square is big. Okay, meter stick make a square. Inch make a square is a very small square. So that's conversion is 1550. So then you put 1550. So the trick is very patiently go from here to this inch square, and then you do the math. And so if you get all of everything set up, so if you press the calculator incorrectly, I will give you most of the credit. So important is you get the concept right. So then that will be 86.787 pound per square inch. In fact, here pound square inch, in fact precisely supposed to be pound force. inches squared. Okay, and so then the additional question is just less than that, and that's what we expect is 86.87 pound per square inch. That is PSI. Well, that ends this exercise.